Chip manufacturing and testing. Hello everyone. Today we will be exploring Lesson 6 of the AIC course on on-chip power integrity. In this lesson, we will discuss the requirements for manufacturing a chip, the manufacturing process, the various stages involved, chip packaging and its evolution, and how the manufactured chips are tested for performance and reliability. Before we delve into chip manufacturing, let's briefly recap the lessons we have covered so far. In Lesson 1, we introduced the concept of system on chip, its needs and benefits. We discussed Moore's law, the evolution of mobile SoC across generations, basic terminologies related to chip design, ASIC design flow, and various applications of a modern-day SoC. In Lesson 2, we discussed power integrity, its importance, and the challenges it presents. We also introduced signal integrity, its necessity, and associated challenges. Lesson 3 provided a basic understanding of the power distribution network, its elements, types of power in an electronic system, and the difference between a system and on-die power distribution network. In Lesson 4, we delve into on-die power integrity, the various checks performed for power integrity like grid weakness checks, where we explained path resistance and effective resistance. Then we discussed static and dynamic IR analysis, where we examined an on-die power network and its components for static and dynamic IR analysis. We then reviewed the mitigation techniques for the issues arising from static and dynamic IR analysis. Lesson 5 explored electromigration, its occurrence, impacts on the chip, and prevention methods. We discussed electrostatic discharge, ESD, its sources, effects, and how chips can be protected from ESD. After all these steps, we need to manufacture these design chips, test their performance, and verify if they match the design simulations. To manufacture chips, specific conditions and environment is required. Unique manufacturing methods are employed, and finally, the chips need to be packaged for their intended use. Take a moment to look around you. Consider how many pieces of equipment, electronics, or gadgets require a chip or a processor. We have evolved as a species, bringing innovations to almost every field. These advancements have led to an increase in the number of devices with a processing unit, affecting the global demand for chips and processors. The trend of making devices smart has led to the inclusion of processors in devices where they were not previously needed. The automobile industry also plays a significant role in increased demand for chips and processing units. The recent pandemic highlighted a shortage of chips, leading to extended waiting periods for cars and other vehicles. Consider a smart car. With its myriad functionalities, in addition to standard features like anti-lock braking system, cruise control, and temperature control system, there would be more advanced features like advanced driver assistance system, internet communication system with a voice command support, and a detailed infotainment system with a smart assistant. This would require a very powerful processor, as the data from all sensors and inputs will be vast and require efficient processing with a very short turnaround time. So, chips have evolved significantly and have become more complex than their predecessors. This constant development across all industries pushes manufacturers to create faster, more efficient, and smaller chips. For this reason, we require improvements and advancements in the chip manufacturing industry to meet the demands and requirements. Before we delve into chip manufacturing, let's discuss some important topics. The data for manufacturing is sent in the Graphic Data System (GDS) file format. This file contains information about the shapes of metals, vias of different layers, and text labels of each layer in the design. This file is used to create the photomask during chip manufacturing. We will discuss more about photomasks in the upcoming slides about chip manufacturing processes. The final design data can also be sent in another file format, OSS, that is Open Artwork System Interchange Standard. Both GDS and OSS files are binary files. It is also important to understand the two major stages in chip manufacturing process, that is front end of line and back end of line. FEOL is the stage where the actual semiconductor devices like MOSFETs, FinFETs, diodes, etc. are constructed. BEOL refers to the manufacturing process where the metal interconnects between these created devices are made. The process of providing the final design of the chip for manufacturing is called tape-out. The term tape-out originates from the time when design data was sent to the manufacturing plant on magnetic tapes. Chips are manufactured in highly specialized plants called chip foundries or chip fabs. Finalized chip designs are sent to these foundries for manufacturing. Foundries require a very clean and controlled environment with a regulated temperature, humidity, and light. These rooms are called clean rooms. Even a tiny particle of dust can cause damage to the chips as the circuits inside the chips are smaller than a dust particle. Vibration can also cause damage or errors in the chip manufacturing process. Hence, the surface on which the raw material is mounted needs to be stable and have vibration damping. A continuous supply of electricity and water is required as both are crucial for the chip manufacturing process. As discussed in Lesson 5, static electricity can also affect the chips, especially during the manufacturing. Hence, people working in the clean room needs to wear proper equipment to protect the chips from damage during manufacturing. Now that we have discussed the requirements inside a chip foundry, let's look at the type of the chip foundries that exist. They are broadly classified into two based on their chip designing capabilities: integrated device manufacturers, IDMs, and pure play semiconductor foundries. IDMs are foundries capable of designing their own chips. They have a dedicated design team that designs chips from scratch, performs simulation and analysis on them, manufactures the chip in their own foundries, and finally sells the manufactured chips. With the latest trend of increasing chip density and complexity, we see fewer IDMs as companies have started to compartmentalize the chip designing and manufacturing process. Pure play semiconductor foundries do not create their own designs. They lend their foundry capabilities to companies that create chip designs. These companies focus on improving chip manufacturing capabilities and introducing new methods to manufacture faster and more efficiently. There are companies that do not have a foundry but handle the designing, verifying, and eventual sale of the chips. These companies are called fabless semiconductor companies. They outsource the manufacturing part to pure play semiconductor foundries. Having discussed the different types of semiconductor foundries and their distinguishing features, let's now delve into the semiconductor fabrication process. The raw material for chip manufacturing is a wafer of the semiconductor material. Depending on the chip, this could be made of silicon, germanium, gallium arsenide, or gallium nitride. The wafer is a very thin round slice with a diameter ranging from 100 to 300 mm and thickness varying from 0.5 mm to 0.02 mm based on the applications. The surface of the wafer is polished on one or both sides depending upon the requirement to remove any surface irregularities. The raw wafer needs to be doped to improve the conductivity. Doping is done by deliberately introducing atoms of an element called dopants. These add or displace atoms from the wafer and introduce an electron deficiency or electron richness in the wafer structure. Doping can be done by diffusion or ion implantation. Various manufacturing processes like lithography, masking, etching, vapor deposition, etc. are performed on the wafer to create the different geometries from the chip design. Let us now examine some chip manufacturing processes that are used by almost every chip foundry. Masking. The entire wafer surface is covered by a light-sensitive material called photoresist. The masking process applies a mask that selectively covers or exposes the required geometries from the chip design so that the photoresist on the wafer will be covered or exposed at the appropriate regions based on the chip design. Photolithography. When exposed or covered from light, the photoresist becomes a soluble material in a special photoresist developer solvent and can be dissolved. The photolithography process applies light on the photoresist on the silicon wafer so that depending on the type of photoresist, appropriate geometries of the design are covered with photoresist before etching. Photoresist can be of two types. Positive photoresist. This type of photoresist will become soluble when exposed to light. Negative photoresist. This type of photoresist hardens on application of light and the regions that are not exposed to light are soluble in the photoresist developer solvent. Etching. Once the required region is covered with a hardened photoresist, we etch the uncovered part as per the design. Etching can be done using chemicals or by using plasma. The photoresist protects the semiconductor material underneath it from the etching process. After etching, the photoresist is stripped off and the entire substrate is exposed for further manufacturing processes. Now that we have understood where a chip is manufactured, the requirements and the types of the chip foundries, and how the chip manufacturing process works, let us look at chip packaging. Chip packaging is the process of encapsulating the chip inside a case. This is done for multiple reasons. As the size of the chips has reduced, it has become difficult to connect to external PCBs. To simplify the connection to the PCB and distribute the power and communication signal from the chip to the PCB and back, we require chip packaging as it provides a manageable port connectivity to the PCB than directly connecting the chip. The chip is tiny and easily susceptible to damage from external elements as well as from electromagnetic radiation. The package protects the chip by acting as a barrier to the physical elements like dust, dirt, or physical contact, as well as acting as a barrier from electrical interferences. Let us now understand the evolution of chip packaging. The evolution was driven by improvements in the chip and the increasing connectivity required to the PCB or the external world. The earliest form of commercially available chips were packaged as dual inline packages. These type of packages were designed in a rectangular shape with the input-output and power pins placed along the long side of the package. This type of packaging was done during the early 1970s. After then, the quad flat package was introduced to increase the pins that could be accommodated on the package. This package was manufactured in a square shape with pins along all four edges. In the 1980s, chips required a much higher number of pins for faster communication with the external world. This meant that either the size of the package would have to increase or a new packaging method would have to be introduced. Therefore, the pin grid array was introduced, in which pins were present at the bottom of the package instead of along all the sides of the package. Hence, the number of pins that could be accommodated improved significantly. As the number of pins from the chip increased, a new packaging method was needed to improve the pin efficiency of the package. As the number of pins increased, the pins became smaller and narrower to the point where they started to break easily. Hence, the wire-bond ball grid array was developed, where the pins were replaced by solder balls. Solder ball connections were easier to accommodate than pins, without any compromise in structural integrity. Also, since they were smaller than pins, inductive effects were reduced, improving thermal capabilities. The I/O and power pads of the chips were connected to the package port through bonding wires. This became cumbersome, especially since solder balls could not be directly placed beneath the chip due to difficulty in routing, which led to wastage of area where pins could be placed. The flip chip ball grid array was introduced to mitigate this issue. The whole chip was flipped so that the entire bottom of the package could have pins instead of just the periphery region. The latest packaging trend is introducing multiple different chips inside the same package so that they are closely placed and communication between them could be faster. This is called heterogeneous integration. In the next lesson, we will discuss heterogeneous integration in more detail, going through advanced heterogeneous integration methods. Now that the chips have been manufactured, we need to test these manufactured chips and that they are free from any defects. Yield analysis is performed to determine how many chips of a wafer are good and how many are defective. A defect is an electrical issue in the chip that occurred during the manufacturing process. Thus, we understand how crucial the requirements that we mentioned in the previous slides are, as very minute variations can cause defects to occur in the wafer. We consider a chip as good if it has no manufacturing defects. A chip is considered bad when there are one or more manufacturing defects in it. Yield is defined as the ratio of the number of good chips to the total number of chips in a wafer. The formula for yield is N good upon N total, where N good is the number of good chips in the wafer and N total is the total number of chips in the wafer. Yield analysis helps the foundry to understand the quality and efficiency of the manufacturing process. After conducting the yield analysis of the wafer, we must test the manufactured chips. This is done to ensure that the chip is meeting the thresholds that the simulated results were showing and to confirm if the chip is indeed functioning as intended. Some of the major tests performed on the chips are burn-in test. This test is used to identify weak chips which pass the initial test after production but fail very quickly thereafter. Functional test. After passing the burn-in test, the chips are subjected to a functional test to ensure the chip meets the desired functionality. This testing and benchmarking helps identify issues with the manufacturing process or the actual design that were not found before. These chips are put through various other testing processes, benchmarked and compared with the values calculated and set as threshold during the simulation stage. To summarize, we discussed what chip manufacturing is, why it is needed, and why it needs to be continuously evolving. We familiarized ourselves with the major requirements for chip manufacturing as well as the workings and type of the chip fabs that exist. We then analyze the various chip manufacturing processes like diffusion, ion implantation, photolithography, masking, and etching. After that, we understood why we required the chip packaging and how far we have come in terms of chip packaging. Finally, we looked at various checks and efficiency tests on the manufactured chips like yield analysis, burn-in test, and functional tests. We hope that this lesson provided you with insight into the chip manufacturing process and associated aspects.